Hello and welcome to another episode of Space Audits. Today I'll be reviewing a research paper that critiques the so called cosmological redshift and how the interpretation of that redshift is used to fit the presupposed model known as the Big Bang Theory, so that model can then be used to justify general relativity. When other just as viable theories exist but are not given the same special treatment the Big Bang Theory is given. Continuing on with the paper, we'll see critiques such as A. A huge bias in science to adhere to philosophical principles. These principles are as follows: 1. The universality of physical laws. This assumption states that the laws of physics don't change from one place and time to another. 2. The cosmological principle. As mentioned earlier in this report, this principle states that the universe is roughly homogeneous and isotropic in space, but not necessarily in time. 3. The perfect cosmological principle. Similar to the standard cosmological principle, although this states that the universe is not only homogeneous and isotropic in space, but also in time. 4. The Copernican principle. This assumes that we are not observing the universe from a preferred location. B. Ignoring other viable models in favor of committing to in- interpreting the observations to adhere to the aforementioned principles. Some of these models are as follows: steady state theory and tired light theory. On the matter of special treatment for the Big Bang theory, things like dark matter and dark energy are invoked to make corrections to the model to keep it in alignment with Einstein's theory of general relativity and the mathematics behind it, even though there is not enough energy in the Big Bang model to account for what Einstein's theory proposes is happening with space time and then how its curvature works. All right, in summary, cosmological models must explain Doppler shift to even be considered viable in modern cosmology. Throughout this paper, you'll learn that there are different types of Doppler shift and what those different types mean and what the different interpretations of those shifts mean for the models of the universe and the theories that they are used to support. The interpretations of redshift within the Doppler effect from light that comes from celestial objects in modern cosmology is the jumping off point where cosmologists can quote unquote theorize about the origins of the universe and how it came to be. With the assumptions that their interpretations are correct, they can then reverse engineer an explanation to match the mathematics of general relativity and keep it all consistent. In this paper, you'll also note that there is a clear bias towards propping up general relativity by reaffirming the Big Bang theory by selectively choosing interpretations of redshift that adhere to philosophical principles like the universality of physics, of physical laws, the cosmological principle, the perfect cosmological principle, and the Copernican principle. When observations are made that falsify these philosophical principles, they are ignored or scrutinized unfairly in comparison with the allowances made to maintain the viability of the Big Bang theory. Namely, variables like dark matter and dark energy being added to account for the lack of energy or force, where no such mechanism is there to explain the lack of energy or force within general relativity or the Big Bang theory to create the expansion that is claimed by these interpretations of redshift that reaffirm the theories. The current favored interpretations of redshift are cosmological redshift, Hubble redshift, gravitational redshift, all of which are important to the cosmological model known as the Big Bang Theory and the origins of the universe, starting from a singularity, adds to the viability of general relativity as it predicts singularities and describes them as physical entities that actually exist. For those that don't know, singularities also exist in Newtonian physics, but everyone knows that they're not physical objects. They don't actually like do anything. They're just a mathematical point, you know. but in general relativity, they're black holes, and all that. So anyway, as flat earthers, we're often told that our criticisms of astronomy and cosmology are unfounded because we're not experts in the field. And the guy that wrote this paper is an expert in the field, and he showcases the extreme biases in modern cosmology that we claim is happening. And he uses a lot of the same criticisms that we also have. So, without further ado, I'll begin reading the paper. A review of redshift and its interpretation in cosmology and astrophysics by R. Gray and J. Dunning Davies, Department of Physics, University of Hull. Abstract. The interpretation of redshift in cosmology and astronomy. In astronomy yields a great deal of information about the universe in which we live, but much controversy surrounds the correct interpretation of the phenomenon. This article discusses the history of the redshift and how its interpretation varies between different cosmological theories, including the Big Bang theory and some of its most famous rivals, the steady state theory and tired light theory, and aims to highlight a few of the problems still existing. Some notions not normally associated with astronomy and astrophysics are mentioned also in the hope that a somewhat broader view of this important topic may be investigated. Introduction. Redshift is a very important and somewhat controversial phenomenon with respect to cosmology and astronomy. The phenomenon occurs when the electromagnetic radiation that is emitted or reflected from an object is shifted toward the less energetic, higher wavelength end of the spectrum. Using this phenomenon allows a start to be made on attempting to understand features of our own galaxy and even the universe as a whole. However, there is a large number of interpretations of this observed phenomenon. This brings into question the nature of these observations and their meanings. One particular case where this is especially relevant in the theories surrounding the origins of the universe. Nowadays, the Big Bang model for the origin of the universe often appears to be accepted as established fact. Its popularity in the scientific community apparently overshadowing all other theories. But is this model necessarily correct? What evidence truly supports this theory over others? Is it in fact fair for this theory to receive so much acclaim when other theories seem to be dismissed without being afforded the same privileges of addition and corrections to their problems? These questions are amongst those to which this article aims to draw attention. There may not be a definitive answer, but a broader view of the problems surrounding these topics may allow an open minded reader the opportunity to make up their own mind on whether or not they want to believe in the conventional wisdom. It is intended to discuss the history of redshift and its astronomical and cosmological interpretations, including the origins of the redshift distance relationship and theory and Hubble's law, making mention of the Doppler effect and how the two are related. This should cover the relativistic Doppler effect, Einstein's general relativity equations, their solutions by Schwarzschild Friedman, Friedman's equations, and gravitational redshift. Discussions will follow some of the views of our universe and more specifically of the theories for the origins of the universe and how the interpretations of the cosmological redshift is important to these theories. In particular, due to its popularity in the scientific community, the Big Bang theory will be considered in some detail, drawing comparisons between this theory and its rivals, such as steady state theory. A brief discussion on one or two alternative theories for the cause of the cosmological redshift will also be included. These may be linked with the theories of the origins of the universe, but we will discuss in more detail afterwards and include the Compton effect, intrinsic redshifts, and tired light theory. History and origins of redshift. Theories regarding cosmological redshift began with the development of wave mechanics in the 19th century and the exploration of phenomena associated with the Doppler effect. This effect is named after Christian Andreas Doppler, who offered the first known physical explanation for the phenomena in 1842. The Doppler effect is one encountered on a day to day basis, though the average person may not understand fully what it is or that they are even experiencing it. It is commonly attributed to sound waves as these are involved in the most commonly encountered occurrences of the effect. Doppler predicted that this effect should apply to all waves. This prediction turns out to be correct. The first Doppler redshift was described in 1848 by French physicist Armand Hippolyte Louis Biezot. I don't know. Who pointed to the redshift in the spectral lines seen in stars as being due to the Doppler effect. In 1868, British astronomer William Huggins was the first to determine the velocity of a star moving away from the Earth by this method. In 1871, optical redshift was confirmed when the phenomenon was observed by Fuller lines using solar rotation about zero point zero 0.01 A in the red. Optical redshift was also verified in 1901 by Arthur Belowski, Belopol, Belopolsky in the laboratory using a system of rotating mirrors. The earliest occurrence of the term redshift in print in this hyphenated form appears by American astronomer Walter S. Adams in 1908, where he mentions two methods of investigating the nature of nebular redshift. This word doesn't appear unhyphenated, perhaps indicating a more common usage of its German equivalent until about 1934 by William D. Sitter. Beginning with observations in 1912, Besto, Siffler, Siffler, Silfer, Besto Silfer discovered that most spiral nebula had considerable redshifts. Then in 1915, Albert Einstein developed his equations of general relativity. These equations, G superscript UV equals minus parentheses 8 pi G capital G over C squared and parentheses T superscript UV. Connect these equations connect matter and energy with the geometry of spacetime. Each superscript stands for one of the four coordinates of spacetime, so what looks like one equation is actually 16. 16 equations. Since some are repeated, there are generally 10 equations. Since some are repeated, there are generally 10 equations. In essence, these formulae describe the laws of conservation, i.e., conservation of energy and angular or conservation of energy and momentum. These equations were solved by Carl Schwarzschild in 1916. The metric found by Schwarzschild is commonly given to the vast majority of textbooks as, and then they have a long equation listed here as figure 1. It describes the space geometry surrounding a spherically symmetrical object of mass m situated at the spatial coordinate r equals 0. This metric gives an excellent description of the space time geometry around objects like the sun and the earth that are, to a good approximation, spherical, and the forms of the basis of their of basis for examination of the three classic tests of Einstein's theory of general relativity. One, the perihelion advance of Mercury. Two, bending of starlight around the sun. 3. The gravitational redshift. Later, Edwin Hubble discovered an approximate relationship between the redshift of nebula, such as those observed by Stilfer, and the distance to them with the formulation of Hubble's law. This law is simply a this law is simply a statement that the redshift in light coming from a distant astronomical entity, for example, a galaxy, is proportional to its distance. These observations corroborated Alexander Friedman's work from 1922, in which he derived the famous Friedman equations, a set of equations that governs the expansion of space in homogeneous and isotropic models of the universe within the context of general relativity. This is considered to be the first This is considered to be the first observational basis for the expanding space paradigm, and today serves as one of the most often cited pieces of evidence in support of the Big Bang Theory. However, it may be interesting to note that Hubble, even upon his final lecture before the Royal Society, always held open the possibility that the redshift did not mean the velocity of recession, but might be caused by something else. Doppler shift. A little more detail. As explained above, the Doppler shift is a phenomenon in which the frequency and wavelength of a wave change for an observer moving relative to the source of the waves. If the source of light is moving away from an observer, then a red shift can be observed. Conversely, if a source of light is moving toward an observer, a blue shift can be observed. If the source moves away from the observer with the velocity v, then ignoring relativistic effects, the red shift given by equation z equals v over c, where c is the speed of light in a vacuum. In the classical Doppler effect, the frequency of the source is not modified, but the recessional motion causes the illusion of a lower frequency. However, for a more complete view of the effect, one must consider relativistic effects associated with motion of sources close to the speed of light. This relativistic Doppler effect is different from the non relativistic Doppler effect, as the equation includes the time dilation effect of special relativity and does not involve the medium of propagation as a reference point. They describe the total difference in observed frequencies and possesses the required Lorentz symmetry. The revised expression for the redshift is 1 plus z equals parentheses 1 plus v over c in parentheses y. This phenomenon was first observed in a 1938 experiment performed by Herbert E. Ives and G.R. Stillwell called the Ives-Stillwell experiment. Since the Lorentz factor is dependent on only on the magnitude of the velocity, this causes the redshift associated with the relativistic correction to be independent of the orientation of the source movement. However, in contrast to this, the classical part of the formula is dependent on the projection of movement of the source into the line of sight, which yields different results for different orientations. Consequently, for an object moving at an angle 0 to an observer, 0 angle is directly away from the observer. The full form for the relativistic Doppler effect becomes, and then they have a new equation here. For the motion solely in the line of sight of 0 equals 0 degrees, this equation reduces to, and they have another equation there. For the special case when the source is moving at right angles, 0 equals 90 degrees, to the detector, the relativistic redshift is known as the transverse redshift. and a redshift is measured even though the object is not moving away from the observer. In the cases where there is a transverse component to the motion, even if the source is moving towards the observer, then there is some speed at which the dilation just cancels the expected blue shift, and at even greater speeds, the approaching source will be redshifted. Expansion of the universe. Initial interpretations of the redshifts and blue shifts of interstellar objects beyond the Milky Way were based exclusively on the idea of the redshift being due to the Doppler effect. However, after Hubble discovered a rough correlation between the increasing redshifts and the increasing distances of galaxies, theorists almost immediately realized that these observations could be explained by a different mechanism for producing the redshifts. Hubble's law of correlation between the redshifts and distances is required by models of cosmology derived from general relativity that have a metric of expansion of space. This idea is different from that of the Doppler effect theory of redshift, in which the photons increase in wavelength and the redshift as space through which they are traveling expands, as opposed to the velocity boost given between the source and the observer being due to classical momentum and energy transfer. This effect is described by the current cosmological model as an observable manifestation of the time dependent cosmic scale factor A in the following way. And then they have an equation that this type of redshift is known as the cosmological redshift or sometimes the Hubble redshift. These galaxies are not receding simply by means of physical velocity in the direction away from the observer. Instead, the intervening space is expanding, which accounts for the large scale isotropy of the effect demanded by the cosmological principle. Cosmological redshifts of z greater than zero point 0.1, the effects of space-time expansion are minimal and observed redshifts are dominated by the peculiar motions of the galaxies relative to one another that cause additional Doppler redshifts and blue shifts. Despite the distinction between redshifts caused by the velocity of objects and the redshifts associated with the expanding of the universe, astronomers sometimes refer to the recession velocity in the context of redshifting of different galaxies or of distant galaxies from the expansion of the universe, even though it is only an apparent recession. As a consequence, popular literature has a tendency to use the expression Doppler redshift instead of the cosmological redshift to describe the motion of galaxies dominated by the expansion of space-time, despite the fact that the cosmological recession speed that despite the fact that a cosmological recession speed when calculated will not equal the velocity in the relativistic Doppler equation. In the In particular, Doppler redshift is bound by the laws of Einstein's special relativity, which dictates that an object cannot travel faster than the speed of light in a vacuum. Thus, v greater than c is impossible. On the other hand, in the case of the cosmological redshift, v greater than c is possible because the space which separates objects, i.e., a quasar from Earth, can expand faster than the speed of light because space is not composed of any material. Can, gr- it can grow faster than the speed of light since not being an object, it is not bound by the speed of light upper bound. Bound by the speed of light upper bound. It's not bound by the speed of light, in special relativity. It's not a physical object. It's not going to run into that paradox where it would have infinite mass or infinite energy or whatever to move it or something like that. Anyway, uh, More mathematically, the viewpoint that distant galaxies are receding and the viewpoint that the space between the galaxies is expanding are related by changing coordinate systems. Expressing this precisely requires working with the mathematics of the Friedman Robertson Walker metric. Gravitational redshift. In the theory of general relativity, there is time dilation within a gravitational well. This is known as the gravitational redshift or Einstein shift. The gravitational redshift of spectral lines is often held to be one of the crucial tests of general relativity. However, the result may also be derived with no recourse to the general theory of relativity whatsoever, nor to the principle of equivalence, as has been shown on several occasions. Redshift in cosmology. Redshift and its many interpretations and variations is a very important phenomenon to consider with respect to cosmology. Its implications are far reaching from the very beginnings of our universe to how it's behaving now, and even the future of our universe, or possibly its end. There is a wide array of different cosmological views and theories, many of which focus on different interpretations of the redshift phenomenon. Covering these ideas, or covering a very diverse spectrum of ideas, a few of these will be considered shortly. The redshift's interpretation is crucial for many, if not all, cosmological theories, as much of the important evidence for these theories is derived and explained starting with the interpretation of redshift. How redshift has been historically discovered and interpreted has been considered, but other views, which will be mentioned later, have also been put forward, and the evidence for and against each interpretation has been presented. If the nature of our universe is to be understood correctly, a more generally acceptable interpretation for the cosmological redshift must be found. Before discussing any specific cosmological theories, the fundamental assumption and general features that these cosmological theories make about the universe must be considered. Several theories may be based upon similar assumptions, but in most cases, the difference between the theories may be as little as a single difference in opinion about a certain feature of the universe, or as much as a complete disagreement about all the fundamental assumptions made by another theory. Historically, cosmology has been in existence as a discipline for thousands of years, though the original cosmological theories were not known as such. Some cosmological theories date back to around 500 BC. For example, atomist universe theory, proposed by Greek philosopher Democritus and Lysippus. These early theories, though flawed by the limited understanding of physics in the age compared with today, paved the way for the theories used today. Einstein's general theory of relativity was used as a mathematical starting point for most of the current cosmological theories, including the popular Big Bang theory, and arguably its biggest competitor, the steady state theory. In order to arrive at a cosmological model, however, theoreticians needed to make assumptions about the nature of the largest scales of the universe. Some of the popular assumptions and features that cosmological theories tend to rely upon are as follows. One, the universality of physical laws. This assumption states that the laws of physics don't change from one place and time to another. Two, the cosmological principle. As mentioned earlier in this report, this principle states that the universe is roughly homogeneous and isotropic in space, but not necessarily time. The perfect, or number three, the perfect cosmological principle, similar to the standard cosmological principle, although this states that the universe is not only homogeneous and isotropic in space, but also in time. The number four, the Copernican principle. This assumes that we are not observing the universe in a preferred location. Some of the current cosmological theories will be considered next, together with the relevance of redshift, the above assumptions, together with possible problems faced by the various theories. Big Bang Theory. Galileo Galilei once said, "In questions of science, the authority of 1,000 is not worth the humble reasoning of a single individual." It seems taken for granted that the Big Bang Theory best explains cosmologies or cosmological observations and the origins of the universe. The average layman often readily accepts the theory because it's the only one he knows. Children are taught about the Big Bang Theory at a young age, with little or no mention to the existence of alternatives. People also have a tendency to follow popular trends, therefore, it is easy for the non physicist to fall into the trap of blindly accepting the Big Bang Theory without question. After all, if so many highly intelligent, well known scientists believe in the theory, surely it must be correct. The aforementioned quote from Galileo gives an important message. Simply because it's a popular theory that most physicists believe doesn't make it the correct theory. It still has its faults and is not necessarily any more truthful than any of the other theories available today, but it does seem to receive an unfair amount of acclaim just for a theory. Being afforded such luxuries as being able to simply alter the theory conveniently whenever a question is raised against it, or invoking hypothetical dark energy I- ideas to explain away discrepancies with the theory. Such luxuries are not readily affordable to alternatives. However, before becoming too wrapped up in what's wrong with the Big Bang Theory, consider what the theory actually entails, how it came to be, the evidence that is considered to support it, and finally, the issues that bring its validity into question. The Big Bang Theory operates on the primary assertion that the universe started at a singularity of infinite density and temperature at some finite point in the past. Observational evidence suggests this to be approximately 13.7 billion years ago. It relies upon that assumption that adheres to the cosmological principle, the Copernican principle, the universality of physical laws, as above mentioned, or as mentioned above, by analyzing the spectrum of light from distant astronomical entities and applying Hubble's law to the observed shift towards a longer wavelength proportional to the object's distance, it becomes apparent that the universe itself is expanding. This is considered to be among the proofs and validity of the Big Bang Theory. According to the most common models of the Big Bang Theory, the universe was originally filled homogeneously with ice and isotropically with an incredibly high energy density, huge temperatures and pressures, and was rapidly expanding and cooling. Approximately 10 to the negative 35 seconds into the expansion, a phase transition caused a quote unquote cosmic inflation during which the universe grew exponentially. After this inflation stopped, the universe consisted of quark gluon plasma, a, a phase of quantum chromodynamics QCD, which exists at extremely high temperatures and or densities. This phase consists of almost free quarks and gluons, which are the basic building blocks of all matter, as well as other elementary particles. An elementary particle is one which does not appear to have a substructure. Quarks, leptons, and gauge bosons fit this category. Temperatures were so high that the random motions of particles were at relativistic speeds, i.e., speeds approximating to the speed of light, requiring special relativity for a scientific analysis of such particles. And particle antiparticle pairs of all kinds are being continuously created and destroyed in collisions. At some point, an unknown reaction term baryogenesis violated the conservation of the baryon number, leading to a very small excess of quarks and leptons over antiquarks and antileptons of the order of 1 part in 30 million. This resulted in the predominance of matter over antimatter in the present universe. The universe continued to grow in size and fall in temperature, typical hence the typical energy of each particle was decreasing. Symmetry breaking phase transition put the fundamental forces of physics and the parameters of elementary particles into their present form. At about 10 to the negative 7 seconds, the picture appears to become less speculative, since the energies of the particles drops to values that can be attained in particle physics experiments. At about 10 to the negative 6 seconds, quarks and gluons combine to form baryons, such as protons and neutrons. The small excess of quarks over antiquarks led to a small excess of baryons over antibaryons. The temperature was now no longer high enough to create new proton proton pairs. Similarly, for neutrons and antineutrons, so a mass annihilation immediately followed, leaving just 1 in 10 to the 10 of the original protons and neutrons and none of their antiparticles. A similar process happened at about 1 second for electrons and positrons. After these annihilations, the remaining protons and neutrons and electrons were no longer moving relativistically, and the energy density of the universe was mainly dominated by photons. This is the moment commonly accepted. This is the most commonly accepted interpretation of the origin of the universe. The three most direct kinds of observational evidence that are claimed to support the Big Bang theory are Hubble type expansions seen in the redshifts of galaxies, the abundance of light elements due to the Big Bang nucleosynthesis, where a few minutes into the Big Bang, when the temperatures were about a billion Kelvin and the density was of that of about air, neutrons combined with protons to form the universe's first deuterium and helium nuclei, and the often cited cosmic microwave background radiation. This was rediscovered in 1965, filling out the entire universe with a thermal blackbody spectrum at a temperature of 2.725 K. This radiation, according to Big Bang theorists, is supposed to date back to approximately 379,000 years after the Big Bang theory, when the electrons and first formed nuclei combined together to form atoms. According to the Big Bang theory, the radiation decoupled from matter and continued through space largely unimpeded. At this point, it is important to mention that the Big Bang theory is not the only theory that is capable of providing an explanation for the cosmic background radiation. In fact, all three pieces of evidence can be applied to steady state theory also. There are, of course, some problems with the theory. During the 1970s and 1980s, various observations showed that there was not sufficient visible matter in the universe to account for the apparent strength of the gravitational forces within and between galaxies. In order to make up for these observations, Big Bang theorists whimsically invented dark matter, which supposedly makes up around 90% of the matter in the universe but does not emit light or interact with baryonic matter. The supposed evidence for the existence of dark matter is that the universe is far more lumpy and contains far less deuterium than can be accounted for without it, and that it has to do with a gravitational influence on other matter. However, to the skeptic, this sounds very much like a convenient way to force the physics to fit the figures, as opposed to actually being evidence for its existence. No dark matter particles have ever been observed. There is a very large number of problems with the Big Bang Theory, too many, in fact, to realistically mention. Even several of the premises that are often held to prove the Big Bang Theory are held by some as evidence against it, including the cosmic microwave background radiation, as according to new evidence, has cool spots, which are said to possibly bring into question the interpretation of the CMBR, since the size of the average cool spot is around the size which had been forecasted for a flat, smooth universe. That not only is the average about right for, but there are far too many spots themselves that are just right with too little variation in sizes. Given the uneven distribution of matter in an expanding universe, Dr. Richard Liu says we should see a broader size distribution among the cool spots by the time that the radiation reaches Earth. Steady state theory. The steady state theory for the origin of the universe is a rival of the Big Bang theory. It was proposed in 1948 by Fred Hoyle, Thomas Gold, and Herman Bondi, working on the assumption that the universe adheres to the perfect cosmological principle as opposed to the Big Bang theory's reliance on the cosmological principle. It has similarities to the Big Bang theory in that it also predicts that the universe is expanding, as it still follows the interpretation of Hubble's law and Doppler redshift, but the steady state theory explains that although the universe expands, its overall density does not change. One of the problems with one of the big problems many people had with this theory is that an expanding universe cannot maintain the same density at all times, as everything would be thinned out. The theory therefore supposed that there was a constant generation of matter, mostly hydrogen, that allowed the average density of matter to maintain to remain equal over time. The steady state theory started to encounter more serious problems as far as most cosmologists are concerned when observations apparently support when apparently when observations apparently supported the idea that the universe was in fact changing. Quasars and radio galaxies having having extremely high redshifts can only be and that they can only be seen at very large distances and not in close galaxies. Please note, this is only if we interpret the redshift as being solely due to the redshift distance relationship. More on this later. The steady state theory predicted that such objects would be found everywhere in the universe, not just in the far reaches, where the Big Bang theory is supposed to have predicted the very thing that was observed. The discovery of the cosmic microwave background radiation was, as Stephen Hawking put it, the final nail in the coffin for steady state theory. The steady state theory explains that the background radiation is a result of light from ancient stars which has been scattered by galactic dust. However, most cosmologists seem to have been unconvinced by this idea, as the cosmic microwave background is very smooth, making it difficult to explain how it arose from point sources. And the microwave background also shows no evidence of features as such polarization which are normally associated with the scattering. Furthermore, its spectrum is also close to that of an ideal black body, that it could hardly be formed by the superposition of contributions from dust clumps at different temperatures as well as different redshifts. A quasi steady state model for the origin of the universe was proposed by Fred Hoyle, Jeffrey Burbidge, J. V. Arlikar, 1993, as a new incarnation of the steady state theory designed to take into account the new discoveries that the old model failed to predict. However, mainstream cosmologists who reviewed the QSS modeled it or model have disregarded it due to its flaws and discrepancies, with observations left unexplained by the proponents. Tired light theories and the Compton effect. The tired light theories are very different from the aforementioned theories in that they don't operate on the premise of the redshift being due to the Doppler effect, nor due to the expansion of the universe. The concept was first proposed in 1929 by Fritz Zwicky, who suggested that photons lose energy over time via interaction with other photons or some novel physical mechanism. One of the successes of the theory was that it predicted the cosmic microwave background temperature to be around 2.8 Kelvin during the time when the Big Bang theory was predicting temperatures anywhere between 5 degrees and 50 degrees Kelvin. A tired light model was also proposed in the 1950s by Finlay, some guy, to explain the redshift of solar lines and anomalous redshifts of stars, as well as the cosmological redshift. One of the remaining problems with the tired light theory is the identification of the physical process through which the energy loss of the photon is brought about. Scientists are still searching for this mechanism, and in 1988, Pecker and Vigor came up with the possibility, drawing attention to the possibility of photons interacting with vacuum particles, which would result in energy loss. Another apparently major problem encountered when considering questions of or about light is the Eris belief that Einstein's special theory of relativity precludes any variation in the speed of light. However, it is important to bear in mind that Einstein's assumptions refer to the speed of light in a vacuum, and it is well known experimentally that the speed of light actually varies according to the medium in which it travels. In a 1985 article, Thornhill showed that the speed of light varies with the square root of the background temperature, which implies it varies in time and would, in fact, slow down with the passage of time. Another idea used to explain the cosmological redshift is the idea that the redshift is due to the Compton effect and has nothing to do with the Doppler effect or universal expansion at all. The Compton effect was observed by Arthur Holly Compton in 1923 and explains that photons lose energy when they interact with matter, thus causing an increase in the wavelength of the photon. Compton scattering usually refers to the interaction involving only the electrons of an atom, although nuclear Compton scattering does exist. Grote-Reber proposed that this effect was responsible for the cosmological redshift in order to explain the observation of bright, very long wavelength extragalactic radio waves. John Caron applied the Compton effect explanation to quasars and the redshift of the sun, which cannot be explained using Doppler shift or the expansion of the universe. These ideas also suggest that quasars might be much closer than their redshift would indicate if they have an intrinsic redshift due to due to being surrounded by a fuzzy atmosphere containing free electrons and other materials. This concentration of electrons produces the unusual redshift as the light travels through it, and it loses energy to the electrons by the Compton effect. If quasars are nearby and they may even exhibit proper motion in the sky as the Earth travels around the sun. Such a proper motion has apparently been seen. There is other evidence there is other evidence in support with the notion that redshift may be due to the Compton effect, which along with more arguments against the validity of the Big Bang theory is illustrated by Karen. Intrinsic redshifts. The idea of intrinsic redshift is the hypothesis that the significant portion of the observed redshifts of extragalactic objects, such as the quasars and distant galaxies, may be caused by a phenomenon other than the traditionally accepted ideas of Doppler shift and gravitational redshift. The most reputable proponent of this hypothesis of this hypothesis is Alton Harp, who noted that many of the astronomical radio sources close to radio galaxies are quasars, high redshift objects are which some are radio loud. Harp proposed the hypothesis that the quasars might be associated with the radio galaxies which themselves somehow ejected the quasars from the galactic nuclei or the galactic nucleus. Quasars which followed this model are described as local, and by extension, their redshifts would not follow Hubble's law. Possible evidence for this includes the case of two conspicuous X-ray sources paired across the nucleus of of the galaxy NGC 4258. Both of these sources were confirmed to be quasars, and there is strong evidence to imply that they are related to the galaxy, such as photographs showing the trails of excited gas emerging from the nuclear regions of the galaxy in the direction of the quasars. It has also been calculated that the probability of the pairing of quasars across NGC 4258 being accidental is only 5 in a million. Other similar cases have been noted, many of which are mentioned in ARP's book, and if such evidence is correct, this shows that the redshifts of the quasars, which is significantly higher than that of the galaxy itself, cannot solely be due to recession velocities. There must be an intrinsic part of to the redshift, and the nature of this intrinsic redshift is unknown, although, as previously mentioned, a suggestion for the intrinsic redshift in the form of the Compton shift has been suggested. However, ARP's hypothesis that quasars are local and contain large intrinsic redshifts has never gained any significant portion or gained any significant support in the astronomical research community. This this is because ARP's work, according to most astronomers, is quote based on a limited number of quasar galaxy associations, and that these associations are merely a result of chance. This opinion is unfortunate, as with the vast majority of astronomical and cosmological research being devoted to the Big Bang Theory and its ideals, very, very little can be done observationally in the way of further proving or assisting ARPS and others' hypotheses regarding intrinsic redshifts, making it all the more difficult for their ideas to be heard. More modern ideas concerning redshift. Although there is little or no mention of it in the mainline astronomical literature, a mechanism for optical redshift being due to, at least in part, correlations among radiating sources and classical interference was first proposed in 1986 by Emil Wolf. This basic concept has been developed extensively and also verified experimentally. It has been pointed out recently that there is a possibility that this mechanism could account, at least in part, for the redshift observed in quasars. This point is important due to ARP's observation, as noted earlier, and is one which needs to be cleared up openly. Gallo has drawn attention to the fact that a Doppler and or space expansion effect will yield similar photon and neutron redshifts, whereas a non-Doppler mechanism arising from an energy loss interaction with intervening matter will result in totally different redshifts for the two cases. On the basis of this observation, an experiment suggested which, if performed, might settle the question once and for all. Current literature indicates further that, that astronomers and astrophysicists might learn much of use from those interested in plasma science. Looking back to the work, both theoretical and experimental, of such as Birkeland and Alvin, Alphen, raises many interesting questions which are deserving of carefully considered answers. Considering the strength of the electromagnetic force in comparison to that of gravity surely indicates a need for the two basic schools of thought concerned with problems of astronomy and astrophysics to come together for an open minded consideration of the problems facing those disciplines today. In the end, all we have are theories which, in many cases, such as the life and history of a star, can never be completely proven or disproven to the satisfaction of all. Therefore, open minded collaboration and discussion are essential if satisfactory progress is ever to be made. A complete re examination of the redshift problem could prove an important beginning. All right, guys, that was the paper. I hope you enjoyed. I hope it gave you some interesting things to think about. And to quote your boy Galileo Galilei, just because all the physicists are saying one thing doesn't mean you have to agree with them. You can use your mind to think for yourself